Chapter 9, Unified Communications and Network Performance Management. Have you noticed the more we go through this course, the more grandiose the names of the chapters get? Unified Communications and Network Performance Management, what's that supposed to mean? Well, it's actually two totally different subjects, right? We've got unified communications, which is made possible by effective network performance management. And we're going to look at both of them. Now, network management is really kind of what the name means. It means managing our networks. It means assessing and monitoring and watching to see what our networks are doing. Knowing how we can find weak spots and finding areas of inefficiency, along with making more areas more efficient and so forth. Making sure that our network does what it actually needs to do, which ultimately is to drive business processes. I mean, that's the only reason IT departments exist. So how do I do this? Boss comes up to you one day, you're an IT person on the staff, and says, hey, is our network running the way it should be? What are you going to say? Yeah, boss, it is, absolutely. Well, yeah, that's probably what you're going to say, but how do you know that? Well, we have ways of determining this, and it's called monitoring network performance. And we have all kinds of tools for monitoring network performance. I mean, built right into Windows, right? We have a tool called Performance Monitor. Let me click on this. And here it comes up, and it has all kinds of these metrics built into it for collecting things for like CPU performance, memory performance, disk performance. The default one right here on this little virtual machine is recording percentage of processor time with 0 to 100% here on the left. And as you can see, our processor utilization, this is time, down below right here. And our processor utilization is pretty low. And I can collect all these different types of data points, right? I can add counters, and I can go in and get information about, oh, I don't know. Let's look at some of this stuff here. Virtual memory, let's say, right? And add that in. Now I've got these other counters in place, and these are virtualization things like ballooning and that type of thing. But this not only gives me a pretty little chart to look at my graphs on, but it records it to a file. And I can take these files, I can export them, I can import them, study them, do all this type of stuff. This is how I gather how my systems are performing. But before I do anything, I got to know what is a good performance. How do I know that these numbers I'm looking at right here are good, bad, indifferent, or otherwise? I don't. I have to find out what normal is. And that's called establishing a baseline. And really, we do this by collecting data over a period of time. And the longer period of time we have, the bigger our baseline is, and the more accurate our data is. Now, this is just some chart of some data of some network traffic gathered over a period. Well, actually, it was over a period of months by the looks of it, at least weeks. And see, I shows I have during different times of the day, I have periods of high traffic and low traffic, high traffic and low traffic. So we know that on Sundays and Mondays, historically, we can expect to have a very low amount of traffic, whereas Fridays seem to pretty much be a high traffic day, right? You have to decide what's normal. So once I have my baseline, I want to continue to monitor. I need to continue to keep looking for changes, right? If this is the pattern I expect to see on a given metric, I need to keep on monitoring to look for changes in this, to make sure that I don't have some weird network spikes on weekends, let's say. That would be an abnormal condition and something that warrants investigation. I have other tools for doing this also. I mean, that's simply a limited server tool. I have a protocol, actually, Simple Network Management Protocol, SNMP. And this is meant to allow me to monitor an enterprise, a large network. And I end up with something like an SNMP server. right? And I have these agents out there that I install on all my nodes, my computers, my servers, my switches, my IP phones, you name it. And they go out there and they collect data, right? And then that data gets reported back to the SNMP server, and then I have one centralized location for all of it. And there's all kinds of products that do this. Most famously, HP OpenView. There's also open source ones like Xenos. There's lots of them out there. You have lots of choices. I also have other logging on my systems. Now, we talked a bit about this last week with our system and event logs. These come in really handy for recording events that we're not there to see. You know, my web server got slow at 2 o'clock in the morning. What's going on with the web server? Well, the fact is I have a system log that I can go back to and look at. Well, the same logging is very useful in terms of network management. And I can totally go out here and open up an MMC console, Microsoft Management Console, and go in and add my event viewer snap-in for this computer. There we go. Let's full screen that. And we can start looking at a few things here. All right, my Windows event logs right here. Expand that. My system log, which is my main system log for this particular system. And it's going to give me all my different events. Here they are, date time stamped in order. And they have ranges anywhere from informational messages, these are those FYI messages, all the way down to error. There was a problem. Right? Well, part of my network management is to go through and monitor these logs on a routine basis. Very commonly, that's one of your morning tasks as a sysadmin. You go in and you go through your system logs. Now, in some cases, you have to go through and do them individually, each server. That can be pretty time-consuming if you have a lot of servers. There's also products out there called log aggregators that collect these event logs from all of my servers, whether I have 5 of them or 50 of them or 500 of them, and puts them all in one place, kind of like an SNMP server does. And it draws pretty little charts and graphs and all this kind of stuff, ways to represent that data more succinctly. I'm also probably going to want to see what kind of traffic is flying across my network. That's really important. From a security aspect, if nothing else, because you want to see what's going on inside your network, but also in terms of performance management, right? Do I have something out there that's flooding my network that I don't know about? So I may put some devices out here. For example, this network tap device, which is really just a fancy name for a sniffer. That I have a server sitting off to the side here. I might have what's called a mirrored port on a switch, which means that it acts like a hub. I turn one port on and all traffic going through that switch goes out that port. And I'll have some traffic analysis program sitting out there, just watching it. So what kind of stuff can I do with this traffic management? Well, for one, it'll allow me to prioritize it, because not all my traffic is necessarily of equal importance. If I don't assign some kind of prioritization, it will be. But maybe I've got traffic, let's say, going to a test machine, a test environment. And I've got other traffic going to my $50,000 an hour in revenue server. Well, I would want to prioritize traffic to my revenue generating server, and the test machine gets whatever it gets. There's actually a term for that. It's called quality of service. We'll look at that more here in a minute. And one of the main reasons we do this, one of the reasons we care so much about what the performance on our network is for unified communication. Really. Now, there's a fancy word, but let's take a look at what that actually means. Back in the day, our offices, and by this I mean like the 1990s, I'm not going back too far here, I would have PCs, right? This is a photorealistic drawing of a personal computer on a desktop. So we had a data network. And we'd have phone systems. Yes, that is a telephone. That's a little rotary dial right there. That's the handset. I can even, if I want to get really fancy, I can even put a little cord in. There we go. There. Now it's a corded phone. And teleconferencing. Teleconferencing is not new. This has been around for quite a while, but with a twist, right? Traditionally, our environments were not converged, which means I had to have 3 separate networks for all of these. I would have my data network for my PCs, right? And I would have, oh, I don't know, let's draw a switch in over here. That's a switch. And that's the only thing that would travel across that network would be data traffic, right? So going across there, and out to a cloud somewhere over here. And then for my phone service, I would probably have something which would have been called POTS. Stood for plain old telephone service. Ma Bell. It had its own network. It had its own series of, we can call them switches, of network devices that my phone was attached to, which in turn would go off and talk to the phone network somewhere. And for video conferencing, same thing. This would be proprietary. I'd have some device out here that I would plug a large screen TV and a camera into. And that would go off on its own cloud somewhere. 3 separate networks for everything. Well, what a pain in the butt this is. Because here's the thing. None of this hardware, none of these networks were compatible. The phone system was a completely different technology than your IP data networks, which in turn were completely different from whatever proprietary video conferencing technology you had. Guess who was usually the person selected to be the phone person? Yeah, an IT person. Hey, Bob, you're not doing much of anything. Go to school for a week, learn this POT system. When you come back, you're in charge of telephones now. Great, thank you very little. Same deal. This proprietary video conferencing system. Hey, Susie, you're not doing anything this week. Go off to this training course for 3 days to learn how to operate this thing. And when you come back, you're in charge of everything video conferencing. Oh, by the way, you still have your regular IP duties and network duties to do also. Pay raise? I don't think so. Well, what a pain. This wasn't good, right? This has been replaced with what we would call converged technologies. And all this really means is I'm using the same network for all different types of my data. I've got data, phone, and video conferencing, all leveraging my IP infrastructure. What I've done is I've expanded it just from a data network. Now it's taking care of phone and video conferencing. Now I don't have 3 separate, uncompatible entire networks, redundant networks I need to take care of. I have 1. And really, IP communications is IP communications. It doesn't matter if that's a data packet, a phone packet, also called VoIP, or a video packet. It gets handled the same way, the equipment's the same way, it's configured the same way. All of it holds true. Telephones, otherwise known as telephony, were traditionally the plain old telephone service, right? Ma Bell. So how do we get that over into a converged network? Well, it's called VoIP, Voice over IP. And all this really is taking voice communications and encapsulating that inside an IP packet at layer 3 of our TCP IP model. That's it. And then it belts off the network just like any other data packet would. When it gets to the receiving side, that packet gets de-encapsulated and turns back into voice communication again. This opens up all kinds of possibilities for me, right? I can still make use of my old desk phones, my old analog ones, possibly, if I have the right equipment. But it also allows me to make use of IP telephones. This looks a lot like a desk phone, might have a little screen on it, but it's got an RJ45 connector in the back. It attaches to my data networks. This is actually a node on my network. It has an IP address, just like my computer does. It's like, think of it as a specialized computer that handles voice traffic. I can also use something called a soft phone, which is just software. Look at our computers nowadays. The laptop I'm sitting in front of right now has microphones and cameras and all this other kind of stuff. Well, if I don't want to spend the money on an IP phone, install a soft phone as a piece of software, and it works the exact same way. It's still IP over a network. Video conferencing along the same line, right? Instead of having our proprietary video conferencing technology using its own protocols that nobody knows what's going on in there, we're encapsulating video traffic over IP. Where we see this a lot is in enterprise anyway, is in video conferencing. Video conferencing is huge, especially since nowadays travel is so expensive and difficult. Have fun making it through security. It's a lot simpler just to get together a video conference. I really have two different ways I can send video via IP. One is streaming, right? And we see this. Gee, there's a service out there called YouTube that is basically streaming video. It's like watching a DVD, except the player is on the other end of the planet somewhere, and I'm remotely hitting play, and the video feed's coming out and feeding on my monitor in front of me. That's all that it is. The other way is what's called the live feed. And it is literally like having a camera somewhere. It is a camera, and is going directly to some kind of monitor. Facebook's been doing this over the last year or so. When you can go live streaming, that's exactly what that is. Teleconferencing generally falls in the live streaming video category, but I can make use of other type of streaming video also. There's all kinds of benefits to realizing this. Proprietary video conferencing equipment was expensive, it was difficult, and you had a lot of compatibility issues. This can allow for cost savings. Just being able to replace face-to-face meetings is huge. The amount you can save on travel is immense. In pretty much any organization where you have people dealing with customers in a professional manner, think law offices, that type of thing, you can expect to be responsible for some kind of video conferencing. So how does this work? How do these different technologies actually function? How do I take voice and stick it into an IP packet? How do I take video and stick it into an IP packet? Well, I make use of something called a signaling protocol, and we have a whole bunch of them. H.323 was the original VoIP protocol. It still exists. There's other ones out there now. SIP, Session Initiation Protocol, is yet another method for doing it. And now keep in mind, these are high-level protocols. These are like layer 5 protocols, right? Remember our TCP/IP stack. These are at the application layer. When I have a converged network, when I have things like VoIP and video and along with my data all traveling across the same network, quality of service becomes important. And we touched on this earlier in this lecture. All that it means is making sure that the certain type of traffic that needs the bandwidth gets the bandwidth. If I don't do anything different, voice, video, and regular IP communications will be treated equally by my network communication. I may not want that. I may make VoIP my most important protocol, right? Maybe video my less important protocol, or maybe video my most important protocol and data my least important protocol. It all depends on what your business requirements are. The point is, QoS allows me to set that, allows me to influence it. The ultimate point of all this, of any network management, is to maintain availability, right? It also means integrity and uptime. Let's talk about what that means. They're all kind of related. The reason our environments exist, the reason IT departments exist, is to drive business processes. If our IT infrastructures are not available, if they are not providing that service, then business processes are not being driven, money is not being made. And from an enterprise perspective, that's really bad. So what really focuses on are these, making sure that our networks have integrity. And that doesn't mean they're fine, upstanding networks. It means that things haven't changed, right? My data on that network is unaltered. Availability, making sure that it's there when it's needed to be there. When some customer clicks on something, they want to buy something and give me a lot of money, and the website goes down, well, I just lost that revenue. And they're very likely just going to go somewhere else. Availability is key. Now, how do we measure availability? One way of doing it is through uptime, right? And what this really means is how many hours over the day is my network available? And we can do it as a measure of percentages. Now, you might go to a vendor and they'll say, you know what, I can guarantee you 99% availability. And that sounds really good. Wow, I'm available 99% of the time. It means you're only unavailable 1%? Sounds good. Sign me up. But spread that out over time. 99% availability means I am down for several days every year. Right? I'm down nearly 15 minutes every day. In some cases, it may not make any difference. 99 may be fine. If your business, however, is generating, $50,000 a minute in revenue, like a big e-commerce retailer would, well, that's not good. This is a lot of lost business. As I bump up, as I raise my availability, notice how my downtime goes down. Now, the holy grail of availability traditionally has been what's called the 5 nines. 99.999% uptime. What that means is you're only down 5 minutes every year. Okay, that's a little more reasonable. Getting to 5 nines availability requires millions of dollars of infrastructure if you're doing it in-house. You're talking about building data centers on overlapping power grids. So just in case one power company loses their circuit, I'm on some other power company also. I'm getting fed by both of them. I'm talking about large enterprise UPSs, large diesel generators, redundant network connections, many different network connections coming in and out of the facility. This is achievable, but to achieve it, you have to have a real need for it to justify the expense of it. There are some general guidelines, though, that'll raise your availability, just in general terms, right? And they're totally Captain Obvious kind of things, like only allow your IT staff on your server operating systems. Well, Likewise, maybe I don't want every IT member to have full administrative access. I may not want the most junior admins to have access for it. I may want to segregate responsibility just for safety's sake, in case somebody makes some horrible problems. Implement a change management system, right? A formal configuration control board where before even your IT staff can change things, they must receive administrative approval for it. Redundant components, we'll look at that here in a second. And the stuff we were talking about before. Monitor the network, right? Look at performance, look at our system logs, that type of thing. When we find errors, fix them quickly. Taking backups and verifying backups of our data and operating systems, making sure that we can come back in the event that a mission-critical server bursts into flames, which happens sometimes, or more than likely stops working for some reason. Disk crashes, fans fail, Bob, the junior IT guy, spills his coffee on it, whatever, right? We need to have a way of preserving our data. And of course, our security policies that we talked about last week, and disaster recovery policies. What do we do in the event that our building or our city gets wiped off the face of the earth? It can happen. One thing I might do to raise my availability is to design my network for fault tolerance, right? What is a fault? A fault is a malfunction of something, like a failed fan, let's say, in a server, That in turn leads to a failure. The server stops functioning. It bursts into flames. I need to design my environments to withstand that kind of loss. Maybe I'll have two servers feeding that same data, sharing the same data. So in the event that one goes down, the other can still be functioning. That's actually an example of redundancy. And we tend to think of redundancy as a bad thing. But in terms of maintaining our availability, we have to have redundancy. It could be something like this, right? Here's my internal network environment, and I have a single T1 connection to the internet. Well, if my business processes depend on that internet connection being in place and always being up, I'm setting myself up for failure. Eventually that will go down for one reason or another. What I might do, though, is have two separate redundant networks connected to each other, or at least two separate redundant connections to the internet. Very possibly using different technologies. Maybe one is going to do T1, maybe one's going to do frame relay, whatever. And also very possibly through two different providers. One will be through Comcast, one will be through Time Warner, right? So if that provider has a problem, the other one hopefully still remains up during that time. I'm going to buy enterprise class equipment. And that gives me things like failover capability, hot swappable components. That means I can pull a component out while the server is still running. Things like hot swappable disk, hot swappable power supplies. This isn't home grade stuff or consumer grade stuff. This is enterprise grade stuff. And it's the reason why the price goes from, a few $100 for a computer to thousands of dollars for an equivalent computer on the surface, because it's enterprise class, because it has hot swappable components. In my internal environments, I might build redundancy into my network connections by something called link aggregation. And this is where I have a server connected to a network switch, and if I have only one connection going over here, let's say it's 1 gigabit connection, that's great and everything, until that cable gets cut. Right? Maybe somebody steps on it and snaps it or whatever. Somebody accidentally unplugs it from the switch, not knowing what it is. If I only have a single cable connection, guess what? That server is isolated. Well, I might have two, right? Two connections going to the same switch, and this might be a form of link aggregation. Now, this buys me two things. I can get fault tolerance, because as long as one is still plugged in, I'm still communicating. Or I could do something called NIC teaming, where during normal operation, traffic is flowing down both connections. If this is a 1 gig connection and that's a 1 gig connection, I've got a 2 gigabit aggregate connection. I need 4 gigabit, throw two more connections on there. Right? That gives me the best of both worlds. Another way is to have multiple switches. Right? I got one connection going to one switch, one connection going to another switch. What does this protect me against? Same idea, somebody cutting the cord or unplugging it, or somebody unplugging the switch. Right? What if this switch dies? Well, I've still got one other switch in there. Other areas that I need to look at redundancy, host name resolution. In one of our prior chapters, we talked about this, DNS. Right? Domain names servers. It's not an exaggeration to say that probably 90+% of all network problems can be somehow related to host name resolution. Your DNS server goes down, especially in a Windows Active Directory environment. Your DNS server goes down, or your hosts are unable to talk to it for some reason. You're going to see all kinds of problems creep up. DNS is very commonly one area where you have multiple DNS servers. Like in this example, I might have a master server with a couple slaves, which this has read-write records, and these are simply read records as one way of doing it. I could set up a DNS caching server that really just learns addresses and hangs on to them. Right? The big thing is you need to have more than one DNS server, even in small environments. No discussion about availability is complete without talking about data backup. And that is to simply take a copy of my data and put it somewhere where it's safe. As expensive as our servers are, expensive as our equipment is, ultimately, though, that's replaceable, right? My data center floods, the river rises, water pipe breaks, whatever, and all my stuff shorts out. Okay, that's bad, but I'm probably insured, for one. And two, I can call up CDW or my vendor of choice and get new stuff shipped out to me. Hardware is replaceable. What's not replaceable is my data, my customer databases, for example. Entire businesses have gone out of business because they've lost their data. Well, the way you work around this is to back it up, make a copy of it. A couple things about backups. It's been said, and I agree with this, backing things up is a total waste of time. What counts is restoring it. And that sounds kind of profound, but that's totally true. I've seen organizations that religiously backed up their data every day for years onto backup tapes. But guess what they didn't do? They didn't test the backup tapes. And when they went and they finally needed it, it turns out that tape had been bad for years and no one ever knew about it. So your backups are only as good as your restores. So this is part of your strategy, right? When you got to come up with a backup solution, hopefully something that's reliable, hopefully something that's under support, an enterprise class solution, Veritas Net Backup, Backup Exec, something along those lines, and find some method to back up to. Tape, disk, maybe nowadays backup to the cloud, right? And whatever method you choose, make certain that you're able to pull it back. So you need to do backup and restore tests periodically, usually at least monthly, bare minimum. And that wraps up our discussion of converged networking and data and network performance management. As always, if you have any questions, please feel free to reach out to me, and I will see you next week.